Okay, so we were looking at graphs, and I think by now you have seen couple of examples of different kind of graphs and so on. You know, their representation. The representation of the graph. Uh, Now, today I am going to discuss about the connectivity of the graph, and then finally we are going to look at two special kind of circuit known as Euler circuit or Hamiltonian circuit. Okay, so these are very important concepts. And given a graph, finding these kind of circuits is a difficult problem. Okay. In fact, you know, the Hamiltonian path problem means graph is given. You have to find a circuit such that, I mean, a cycle such that you pass every vertex exactly once. So this is a Hamiltonian circuit. Edelman actually gave a solution to this problem, a special case actually, using DNA computing. So he used bunch of DNA molecules to show that you can actually solve Hamiltonian path problem. It was really interesting thing. And this was the year 1994. So I hope some of you were born or not. Okay. So I was doing PhD, so I was very excited. It was 1994, so I looked at that paper, and so some of you actually who are asking for what to do in the project, still they are undecided, right? So you can pick up anything at this intersection. For example, graphs can also be used for classifying the proteins. Okay. The proteins classification can be done. There is something called as protomap. You can search on Google, you can find. You can also look at, see, most of these viruses which infect you, like this coronavirus and everything, most of the deadly viruses are made of RNA. Ribonucleic acid. RNA is a beautiful molecule, and there is a very nice book, RNA World, which you can look at it in order to see whether there was a life before. uh, you know so so normally RNA came first, then from RNA DNA came, and then from DNA everything else, all the proteins. So there is a central dogma of biology which says that DNA gives you RNA, RNA gives you protein. Okay, this is central dogma of molecular biology. So double load of RNA was discovered by Thomas Eck, and he got a Nobel Prize. That these RNA molecules can also act as a catalyst to certain chemical reactions, and also, you know, uh, they are part of this central dogma actually. So it's a very interesting topic actually. So if you pick up RNA, so now if some unknown virus is there, so basically this RNA molecule folds into a specific kind of a structure because of the bonding between the ACGT. Okay, and once it folds into a specific kind of a structure, you can classify those structures. So some of the RNA secondary structures for many known viruses is still unknown, open problem. Okay, so maybe, so in fact, one of my student has written a program to classify these RNA molecules using graph theory. So again, so a lot of interesting things are possible if you really want to look at biology, because you can actually do wonders. So anyway, so that's just some information. So let us look at this connectivity issue in a graph. Okay, so let us look at this graph. A, B, C, D, E. We have this graph here. So, I need to find a cycle. So I can see that A, B, D, and E is a cycle, right? Can you see these things? Slides, do you know? Back and right. Good. Okay. So now you can see that A, B, D, E. This is a cycle, right? This is a cycle. Okay. We can walk around this cycle in the graph. A, B, C, D, E. Is this a cycle? A, B, C, D, E. It is a cycle, right? You can walk like cycle, right? What about B, E, D? Is it a cycle? B, E, D. So now B, E, D. I mean, of course, it is not a cycle. You cannot walk, right? You cannot jump. So this is not a cycle. Let us look at another example. A, B, C, D, E, F. So graph is like this. A, B, C, D, E, F. So, and these are the edges, This is not there, I think that's the problem. So now I need to find some cycles. So I'm just asking this question or path basically. By the way, both of these graphs are simple graphs, right? There is no loop or multi-edge. A, D, C, A, D, sorry, F and C. You can see that this is a simple path, right? A, D, E, F, C. It's a path. It's not cycle because it's not coming, not including everything, right? But it is just a portion of. So a portion of cycle is actually a path, right? Of certain length, right? How many edges are there? You can count. Or how many vertices are there? What about this? D, E, C, A. Is it a path? D, E, C, A. Is it a path? No, right? Because there is a, you need to jump. So this is not a path. What about B, C, F, E, E, B? This is a circuit of length 4. So B, C, F, E, and B. So 1, 2, 3, 4. It's a circuit of length 4, right? Circuit of length 4 because there are 4 edges. Okay. Okay, one last question. A, B, E, D, A, B. Is it a path? A, B, E, D, A, B. So what is happening? This edge is coming twice, right? So basically, this is not a simple path. Of course, it is a path, but it is not a simple path. A simple path contains only one edge when you walk. Okay. I'm just giving you examples and the definitions, right? So I hope it is clear to you. Because edge AB is coming twice. Okay. Let us look at another example. A, B, C, F, E, G, E. This is a graph. Another graph is A, B, C, and D, E, F. These two graphs are there, G1, G2. Which one is connected graph? Huh? G2 is connected? Connected means, we can walk from, one vertex to other vertex without any problem, right? So can I here, so if I start from G, I can go to B. If I start from A, I can come to E. If I start from D, I can walk, right? It's all connected. Whereas that graph, G2 is not connected because there is no path from C to D or B to E, right? So that is a disconnected graph. And this is connected graph. So a graph is connected if there is a path between every pair of vertices. Simple thing. Okay. So I think you got an idea of, from this picture, you got the idea of cycle or circuit, right? Cycle or circuit means, you're walking and completing a circle, right? Starting from one vertex, walking along the edges, right? And completing one circuit, right? So now, so there are a special kind of circuit that we are now going to talk about. One is known as Hamiltonian circuit, and another one is known as Euler circuit. Graph theory started uh, from this idea of finding Euler circuit. Why it is Euler circuit? Because Euler actually asked, there was a special kind of graph. I mean, in Germany, there is a river and there are 7 bridges, and you have to walk across the bridges. So just you don't go twice on anything, right? So I think, let me give you definition. An Euler circuit is a graph G. An Euler circuit in a graph G is a simple circuit containing every edge of G. Every edge of G. So let us look at an example. A, B, C, D, E. This is a graph. Okay. Now you can check that A, E, C, D, E, B, A. Is it a circuit? Starting from A, go to E, go to C, go to D, go to E, go to B, and go to A. I am duplicating the vertex, but I am traveling every edge exactly once, kind of thing, right? Every edge is only one, right? So starting from A, and I am coming back to A. So it's a circuit, and it contains every edge. Okay. If every edge is there, so that means this is known as Euler circuit. What about this graph? A, B, C, D. The question is, find the Euler circuit here. Can you find Euler circuit in this graph? Starting from a vertex and try to walk around the picture, right? So that so you will see that it is, I mean, there is no such thing. I mean, you cannot find Euler circuit no matter which vertex you start and try to find a circuit. So it's a good example for you to look at it, right? This graph has no Euler circuit. Similarly, if you look at this graph, this has no Euler circuit. Okay. But this graph has an Euler path. Euler path means complete circuit is not there, but a portion of it. So A, E, D, sorry, A, C, E, E, D, D, A. So this is an Euler path, but there is no Euler circuit. Not coming back to the original vertex, right, from where you started. Okay. So there might be a possibility that the graph has Euler path, but no Euler circuit. Okay. In fact, there is a result. I mean, in fact, there are two results which I would like to mention here now, without proof, of course, that, you know, okay. So remember, Euler circuit means every edge should contain every edge, right? That is important. So basically, there is a result, a connected multigraph with at least two vertices has an Euler circuit if and only if each of its vertices has even degree. I think when we started this class, I draw one picture similar like that. So when we were trying to draw it without lifting the pencil, right? So the same thing is trying to find a Euler circuit, right? So in that picture, we cannot draw the Euler circuit because the degree of vertex should be even for each degree, right? Which is not the case. Okay, so that is the main reason. So I think, for example, if you look at this, A, B, C, D. This is a multigraph. Now you can see that degree is not even. Degree of D is odd, right? So basically, this has no Euler circuit. In fact, there is one more result. Connected multigraph has an Euler path, but not an Euler circuit if and only if it has exactly two vertices of odd degree. So a connected multigraph has an Euler path, but no Euler circuit if and only if it has exactly two vertices two vertices of odd degree. In fact, so this is kind of to identify Euler path. First result that a connected multigraph will have a Euler circuit if and only each of its vertices has even degree. I mean, I think this is something one way is fairly straightforward because if it has a Euler circuit, right? So it will visit. I mean, it will have every edge right? When you walk around a path. So basically, if you are entering on a vertex, you will also go out of the vertex. So degree of the vertex will be even anyway, right? So when you enter on a vertex, you will also go out because it's all connected as well, right? So degree will be even. So one side is easy, other side you can look at, I mean, you can take a cup of tea and try to prove it, right? Anyway, so this is all about. Let me give a couple of more examples to you. A, B, C, D. So B and D are odd degree, right? Degree of B is same is 3, same thing as degree of D. There are two vertices of odd degree here, right? From the previous theorem, and of course you can see that it has Euler path as A, B, C, D. So this is the Euler path. Starting from A, you go to B, come to C, come to D, and goes back to B. Since we are not going back to A, you're right. So it's a Euler path. Every edge is there, right, in this path. Okay. So I hope if you understood everything. Let us look at this example. This is a graph. Can we find Euler path in this graph? Euler path. You saw the result. A graph or multigraph will have an Euler path if and only if there are two vertices of odd degree. How many vertices are there here for odd degree? 6, right? Yes. What? I'm going from A to B, B to C, C to D, D to B, right? So it's a path actually, right? It's a path. It's not a circuit. Complete circuit is not there. Huh. So what I'm saying that actually 1 minute. So basically, a path is where actually look at the previous figure. Okay, so we started from A. Can it has any other Euler path? Which one? D. Next. A, B, C, D, and B. Yeah. So I think this is not a Euler path. I mean, okay, fine. But this is an Euler path, right? What about this graph now? So no Euler path in this graph because there are 6 vertices of odd degree. Okay. Okay. So I think that's all about Euler's path. Now we can look at Hamiltonian path or Hamiltonian circuit. Look at the graph A, B, C, D, E. Now this graph has Hamiltonian circuit. So Hamiltonian circuit means each vertex exactly once. So A, B, C, A, B, C, then D, then E, right? So starting from A, B, C, D, E, A. So this is a Hamiltonian circuit, right? Hamiltonian circuit, because it contains every vertex exactly once. There it was edge, here it is vertex. If you look at another example, A, B, C, this has no Hamiltonian circuit, but A, B, C, D, and B. No, B will be there. A, B, C, D. Yeah, so this is a Hamiltonian path, A, B, C, D, right? Because it is covering every vertex, okay, and not completing the cycle. I think I can give you few more examples. A, B, C, D, E. Can you find Hamiltonian circuit in this graph? You will see that it has no Hamiltonian circuit actually. Or if there is a graph like this, A, A, B, C, D, E has no Hamiltonian circuit. Okay, so the question is when we'll have a Hamiltonian circuit. There is a theorem. I'm just mentioning it. If G is a simple graph with n vertices such that every vertex in G forget about. I think it is. You can leave it actually. I think Anyway, I think there are two results, but they are kind of advanced. I think you can skip it. One is due to Dirac, another one is OR. So anyway, so this is all about circuit and path, the connectivity. Now we can actually focus on trees. Trees, I hope you already know about trees, but we'll see few things. A, B, C, D, E, F. Is it a tree? A tree, is it a tree? Or we start with A, B, C, D. So, is it a tree? I think I can mention a definition. What is a tree? Is a connected, undirected graph with no simple circuits. So, is this a tree? No, because it is not connected. It's disconnected, right? What about this? Yes, this is a this is a tree. This is not a tree. What about this graph? A, B, C, D, E, F. Is this a tree? Why it is not a tree? Because E, D, A, D, E is a circuit. Right? So tree should be, free from a circuit. So these are examples of tree. I think I can now look at one more example here. A, B, G, F, D, E, C, H, I, J, K, L, M. This is a tree. This is a rooted tree because A is the root, right? I think you know these things. Now, there are certain definitions that are coming. What is the parent of C? Parent of C is B. Fine. The children of G are H, I, J. Fine. Okay. The ancestors of E are C, B, A. Very good. This, and this. The descendants of B. Okay. Very good. The internal vertices are A, B, C, G, H, J. These are internal vertices, right? Outsides are leaves anyway. The leaves are D, E, F, I, K, L, M. And if I break this thing from here, this will be nothing but subtree. Subtree rooted at G. Right. Now I am going to do one result. I think that is important. Or probably you know already. Theorem is a tree with n vertices has n minus 1 edges. A tree with n vertices has n minus 1 edges, right? And proof is by induction. The base case n is equal to 1. If there is only one vertex, there is no edge, right? So this result is true. Induction hypothesis. So suppose that every tree with k vertices has k minus 1 edges. Suppose k is positive here. So suppose we have, thing like this. Suppose this is a tree T prime having, k vertices, okay? So this is T prime. I'm saying that T prime has this is a tree T. T prime has k plus 1 vertices, right? Sorry, uh, T has, suppose T has k plus 1 vertices, right? I have to count the number of edges. Okay. Now T prime has k vertices. So k minus 1 edges. It will have k minus 1 edges, right? So one edge is left. There is only one edge. Okay. So therefore T will have k minus 1 edges of T prime plus 1 edge is equal to k edges. This is easy proof, by induction. So every T with k vertices has k minus 1 edges. Okay, that's the induction hypothesis. So we have assumed that suppose there is a tree capital T which has k plus 1 vertices. So we can separate out T prime which has k vertices. Those k vertices will have k minus 1 edges. This one edge is extra, so total edges will be k edges, right? So this is easy to prove. I think what else is left? Okay, so I think I'm now going to tell you something about what is known as prefix coding. Okay, or prefix code. These are quite useful in Huffman coding, or whatever. So basically, so we know that in English, in any running English text, E occurs quite often, right? So we assign a short. So suppose you want to encode a string. I mean, we want to encode a text. So whatever character is occurring most, I'm going to assign less number of bits. Okay, whatever is more, I'll assign, so whatever is occurring more, I will assign less number of bits, right? So we will, with this principle in mind, we can actually do encoding. So I think these codes are known as prefix code, how they are used. I'm giving you only an example, okay? So it is done by a tree. So E0, 1, there is a child. This is left child. This is right child. Okay. Then here we go A, 0, 1. So when we are moving towards left, we are assigning 0. When we are moving towards right, we are assigning 1, 0, 1, 0, 1. And so from this kind of tree, I can encode Eve as 0 because only 0 bit is there. This one. Then the next one is A. A is 1, 0. So basically, we are coming from here. This 1 and this 0 is for A. Okay. Then for T, 1, 1, 0 and 1, 1, 1, 0. For S, 1, 1, 1, 1. Okay. So this is known as prefix coding. Okay. So in fact, the decoding is also done in a similar manner. So if we have 1, 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, I can make these groups, S, A, N. Okay. If this kind of bit strings are given, so we can actually do this kind of prefix coding. I think I'm just giving you an example. I'm not showing you all the full thing how it is done, but just an example that how prefix codes are assigned, to alphabets. Anyway, so basically, Now I'm going to describe Huffman coding, but not today. We'll do it in the last class, which is in the next. Huffman coding and few more things on the trees. That's all I think. If you want, we can cover more applications actually, but it's up to you actually, right? Don't want?